Okay, so as I told you already last week, so for the midterm, which will be next week on Thursday, the material which will be covered by the midterm is everything from the beginning until what I taught last time. So what I'm going to teach today and on Thursday will not be part of the midterm, but then of the final, of course. Actually, we finished now already chapter 13. And if you remember at the beginning of the lecture, I told you that this semester we have, you can roughly say, 3 big topics to cover. The first one was series. This we have discussed in the first about a month, and then we have spent some time discussing calculus for vector functions. Now, what we want to do with the remaining time, with the remaining 2 months, is we want to extend everything, more or less everything what we have discussed last semester to functions of 2 and more variables. So now we are looking at a function which so this is different from the last chapter where we looked at the function which mapped the real numbers onto vectors. Now we look at functions which map vectors here, because you can say, you can interpret this as a vector. So you have as the argument of the function, you have a vector xy, and the vector is mapped onto a real number. So we look now at such functions, and so most of the time we will concentrate on the case where we have just 2 indeterminate variables, but of course we will also look at a more general situation where we have more than 2 indeterminate variables. So most of our result will also hold for the case where you have more variables, for instance 3 or even more than 3. The reason why we look most of the time at this special case is because here at least we can still draw things, whereas if you allow three independent variables here, then you get something which is in the 4-dimensional space, and you cannot draw it anymore. What we essentially want to do is we want to understand, okay, for instance, what does it mean that such a function is differentiable? First, we of course have to discuss what does it mean that such a function is continuous. Therefore, we have to define limits, and later on we will also figure out tools how to find, for instance, extreme values of such functions, and so on and so forth. This is essentially what we will do in chapter 14, where we will discuss differentiability, continuity and differentiability of such functions. And then in the final section, chapter 15, we will discuss integration of such functions, functions of more than 1 variable. So this everything what we are going to do in the next 2 months has to be compared with what I have done already last semester, and we will see that some things will be pretty similar, but because of the new, because we are going up, we are going up from the first dimension into here. We have for the domain we have the 2-dimensional space, so things will get more complicated. So we will see that many things are the same, but there are also new phenomena which will arise. Now, the first section in chapter 14 is 14.1. I will just very roughly go through this section because I think most of the things which are introduced in this section are quite trivial. In particular, you see that the author in the section 14.1 starts with the definition of such a function. I don't think we have to define such a function. It should be pretty clear what such a function is supposed to be. And of course, we have all the notation which we are used to from functions of 1 variable. So we will have a domain, we will have a range of such functions, and we are interested in understanding such functions. Now, you also find in section 14.1 some examples for such functions, which should convince you that such functions are important in application. But I guess everyone is going to believe me that in application there are functions which depend on more than just one variable, the situation we have discussed last semester. In fact, most of the functions will depend on more than just one variable. For instance, if you are interested in the temperature at some point on the Earth, then you will, depending on which quantities you are going to take into account, but for instance, you can look at the temperature at the point on the Earth as a function of two variables, if x and y has the meaning of latitude and longitude. You can also look at it as a function of three variables if you introduce the standard Cartesian coordinate system. And you can also look at it as a function of four variables if you take time into account. So if you are interested in what is the temperature at some point on the Earth at a specific time. So this would be one example. Of course, other examples like this here. This is one which you find in our textbook. So normally, if you write down something like this here, the domain for us is just all points x and y where this is defined. So which is in this case very easy. So the domain is the set of all x and y, where x squared plus y squared is smaller or equal than 9. Okay, so the domain of this function is just everything what is a disk with radius 3. You find also other examples in section 14.1. Some of them are quite interesting. You have there an example which is not given, of a function which is not given by such an expression, so-called wind chill factor, where what you are interested in is, for instance, in winter, if you are outside, then if you just look at the outside temperature, then you from the outside temperature you can deduce whether you will feel cold or not. But another factor which has an impact is wind. If there is wind, then it's even so if the temperature is not that low, it feels much colder. It's something which we experience here in Jinju in winter. If the wind is blowing, then it's much colder than in other places like Taipei. And the so-called wind chill factor takes this into account. So you find this function in our textbook, one of the examples in section 14.1. So in this case, the two variables have the meaning of, one of them is what is the actual temperature outside, and the other one is what is the velocity of the wind blowing. And from those two data, you compute, or you have a temperature which you actually feel, so your subjective temperature. And this is so-called wind chill factor. And you have other examples in our textbook. Another one is a model for the American economy from 1899 to 1922. You can take a look at this example. Also, this will lead to a function of two variables. But I think I do not have to spend too much time to motivate such the use of such functions. Now, of course, normally what we do in if we have a function of one variable is we want to have a picture of the function, because from the picture we will normally see quite a lot of properties. This is what we are used from high school. So if you have just one variable, then normally you plot the graph. Of course, for such a function, you have a graph as well, but the graph will be in the space. The graph normally, in mathematics, the graph, the precise definition of the graph is the graph for us is not the picture. The graph for us is a set, the set of all points x, y, and z, where x and y are in the domain, and z is equal to f of x, y. So this is the graph. And for instance, for this one, okay, it would be possible to plot the graph without having a graphing device. Because you see, this is one of the quadratic surfaces which we have classified before. And you see that, so this one is the elliptic paraboloid, but it's not in the standard form. So what you are going to do is you plot here the graph, the circle with radius r is equal to 3. So here you have the point 3, and then you have something like this here. Okay, so the graph of this function here will be given by some part. Actually, this is not really a elliptic paraboloid. So it's just some part of the elliptic paraboloid. So you get just this part of the elliptic paraboloid. This is one way to depict such functions. Of course, this kind of methods you will feel yourself limited very, very quickly unless you have access to a program like Maple, and it will not be easily possible for some very complicated. If I give you a complicated expression to plot the graph like this, and this is essentially also the difference. One of the big differences between discussing functions of one variables and discussing functions of more than one variable. That most of the time you do not have a picture, whereas for functions of one variable, most of the time you understand how the graph roughly looks like, and you can deduce properties just from the graph. Another way to plot functions of more than one variable is using so-called level curves. So here you actually plot. The graph here, or you depict this function not in the space, but you do it in the plane. So what you're going to do is you just plot the curves, all the curves where the set value is constant. So these are the cross sections of the graph here in the space with the plane which is parallel to the xy plane. So for instance, you see that okay, if you look at the circle which has radius 3, then all those points have the same function value, namely 0. So you write 0 next to it. And if you choose a smaller circle, something like this here, then also all the points on this circle will have the same function value. And the smaller the circle gets, the larger this value gets here, which you write here. So for instance, okay, so here, okay, so you have different ones, and the last one is equal to 9. And plotting depicting this function like this here, okay, also tells you somehow, if you have enough information, also gives you some way to understand how such a function behaves. Indeed, such level curves, also Maple is able to plot such level curves for a given function, but since Maple is very powerful in plotting the actual graph of such a function, it's not really necessary in many cases to plot the level curves. This kind of plotting such a function by plotting its level curves, something which we are already used to it from, for instance, geography, where normally if you depict height differences in a country or of some area, then normally you use a similar way in order to do this, also by level curves. So you plot normally, but normally you use different colors. So you plot all the points where the height is the same in the same color. Okay, so there are two ways in order to plot such functions. One is plotting the graph, which is then in the space, and another one is plotting the level curves. Okay, so this is a function of two variables, but we are going to look also at functions of more than two variables, for instance, 3 variables. For instance, an easy example would be omega is equal to x squared plus y squared plus z squared. But of course, here the situation is of course different because here you will not be able to plot the graph because the graph will be in the 4-dimensional space. What you still can do, if you look at functions of three variables, is you can plot the so-called level surfaces. which are the surfaces of points x, y, and z, where the function has the same function value. For instance, for this one, you see all the level surfaces are given by spheres, which are getting larger and larger if the common function value is getting larger and larger. And this somehow helps you to understand how such a function behaves. But of course, it is not so convenient as having the graph, which is not possible in this case. And if you go on to functions of more than 3 variables, then you do not even have something like the level surfaces. So if you go on to functions of more than 3 variables, you won't have any picture. You won't have access to any picture of the function, which normally makes discussing properties of such function much more complicated than functions of 2 variables. So most of the time, for the sequel, most of the time we will look first at functions of 2 variables. We will try to understand, for instance, how to define that such a function is differentiable. What is a good notation that such a function is differentiable? And once we have figured out the situation for this case, we will just use the same definition for higher dimensions. But the interpretation in some cases might be a little bit different. But we always use this case here, functions of 2 variables, just because of the reason, because we have a picture. We still have a picture here of the function as the situation where we start. Okay, so as I have explained, what we want to do is we want to define what does it mean that such a function is differentiable. But the first thing, if you remember, the first thing we have defined last semester was the limit. So first you need a limit, then you can define continuous functions, and then you can try to figure out what does it mean that such a function is differentiable. So the first notation we need are limits. So the first thing we are going to define are limits for functions of 2 variables and for functions of more than 2 variables. Okay, now let's look at some examples. Okay, so I have a couple of examples here. For instance, this one. Then this one. Here you have another one. Okay, so here you see a couple of functions. You will notice all those functions are not defined in the point 0, 0. Okay, so what we want to understand is, okay, if we approach the point 0, 0, okay, what does happen with the function values? Same as we have done last semester for the limit. Okay, so you are now in the xy plane. You see that the domain of all those functions, all points in the xy plane without the origin. Okay, and you want to understand, okay, if you approach the origin, no matter how you approach it, okay, does the function value approach one value? Okay, but you see that compared to what we have discussed last semester, you have here many different ways of approaching the origin. You can something like you approach like this here. Okay, or you can or you just approach along the x-axis, for instance, like this here, and so on. So you have different ways of approaching. Okay, now if you do some experiments, so for instance, you take the first function, you make you approach the origin, okay, along different passes. You will figure out, no matter how you do it, okay, for the first one, as x and y both are getting small, the function value seems to tend to 1. Okay, for the second one, you will see, okay, no matter how you approach, okay, the function value seems to tend to 2. And for the last one, okay, you will notice that actually if you approach, okay, it will depend on how you approach, okay, to which value the function value will tend. Okay, so but you have something similar here to the limit. Okay, so for the first one, okay, we will have the guess that the limit xy tends to 0, 0 of f1 xy is equal to 1. For the second one, we will have the guess that the limit xy tends to 0, 0 f2 of xy is equal to 2. And for the third one, we will have to guess that the limit xy tends to 0, 0 of g of xy does not exist. Now, you see the obvious thing we have to define first is what do I mean by such a limit relation? Okay, we have defined this last semester, but for a function of one variable. So if I have a function of two variables, what do I mean by such a limit relation? You see, kind of, okay. So this kind of means, okay, if this limit is equal to 1, okay, this kind of means, okay, if you approach the origin, okay, no matter how you do it, okay, you will always the function values. You will always observe that the function values are getting closer and closer to 1. Okay. Whereas here, for this here, you will observe that if you approach differently, you might get different values, or even you do not have any convergence. So you make your x and y both simultaneously smaller and smaller. Okay, and you want to understand what happens, okay, with the function values. Now, so first we have to define precisely. I shouldn't erase this because I need this. First, we should give a precise definition of the limit, and for this, we just use the same idea as last semester. So we give an epsilon delta definition. Okay, so just what I just said in words. Okay, we translate it into a mathematical language. So if we have such a limit relation, what does this mean? If you give me an epsilon, or if I give you an epsilon, then you have to give me an and now you see here some domain, okay, which is small enough, okay, and contains the origin such that for all points x, y inside this domain, okay, the distance between this function and 1 is smaller than epsilon. And for the domains which we choose here are, for instance, disks, okay. So if I give you an epsilon, you have to give me the radius of the disk, okay, such that for all x, y inside the disk, okay, the distance between the function value and 1 is smaller than epsilon. And this is just the same definition as last semester, but now for functions of two variables. Okay, so let's look at the definition. Okay, so we will use this notation, the limit xy tends to, more general, AB, f of xy is equal to L. What do we mean? We mean that for all epsilon larger than 0, there exists a delta which might depend on epsilon, such that if x and y are close enough to 0, okay, and closeness to 0 of a point in the plane, okay, we measure by the Euclidean distance. Okay, so if for all x such that the distance to the point AB, okay, larger than 0, because we will see in a minute why. So the point xy is not equal to the point AB, okay, smaller than delta. There holds that f of xy minus L smaller than epsilon. Okay, so this is just the same definition as last semester, but translated into the new situation where you have functions of two variables. Maybe if you look at such a definition, you might have the feeling, okay, why not just defining? Okay, I just use two limits, right? I first maybe with respect to y, and then with respect to x. Okay, why not like this? And the two limits, okay, because you see that for this one, okay, I compute the limit, of course, for all x, and then I compute the limit with respect to x. Okay, so why not doing it like this here? We will see that there is a difference, okay, between this here and this here. Okay, so sometimes in some cases, okay, what you get here will be the same as what you get here. Okay, but in some cases not. Okay, so it's not this symbol here is really a new symbol. Okay, it's not just two limits. I will come back to this when I will discuss such examples. Then we will see that if you want to compute this limit, okay, it's not just that you first compute the limit with respect to y and then with respect to x. We will see that the limit first with respect to y and then with respect to x, and the limit first with respect to x and then with respect to y can be different. Okay, so this is the definition. You see some interpretations of this definition, graphical interpretations in our textbook. So, for instance, if the graph of the function if this is the graph of the function, and let's also plot the domain. So let's say this is here the domain. So this is the domain of our function, and we have a point AB. The function is not necessarily defined at this point. Okay, that's why because I exclude here the case where x and y is equal to AB anyway. Okay, so the function is not necessarily defined. Okay, like here, all those functions are not defined at the origin. Okay. Now, what does this definition mean? So you see that here the limit should be just on the just this one. Now this means, okay, I give you an epsilon. Okay, so what does the epsilon mean here? The epsilon means okay, we plot this point here. And this here will give you an epsilon interval around L. So what you have here is something like this here, where you have epsilon. Okay, and what you have to give me now is a disk, okay, around the point AB. So for instance, this one. Okay, such that small enough, such that all xy which are inside the disk. Okay, if you look at the function value, fall inside this epsilon strip. Okay, but this epsilon strip here, in this case, of course, not a strip. It's like two planes. It's three planes. Okay, so this one is a plane and this one is a plane. It's pretty similar to what we have done last semester, but now, of course, more complicated to draw. Okay, because everything is in the three-dimensional space. Okay, but it's similar to last semester. This is the definition with. We will start from this definition, okay, and we will figure out, okay, how to compute limits starting from this epsilon delta definition. So I guess you remember the approach last semester. So what we have done is, okay, first we have given the epsilon delta definition, then we have figured out for some easy functions what is the limit. Then we have proved some laws, some so-called limit laws, and then we use the limit laws in order to figure out more complicated limits. And essentially the same approach we are going to take here. But first, I want to discuss, okay, how to show that limits do not exist. For instance, how to show that this limit does not exist. Now, you remember using the epsilon delta definition to show that the limit does not exist is always pretty complicated. But last semester we had an easy method which worked in some cases to prove that the limit does not exist. Namely, last semester we showed the following theorem. This limit relation holds if and only if the left-hand limit is equal to L and the right-hand limit is equal to L. For instance, this very easy fact, okay? If you look at the function which is which is 0 for negative x, and then jumps to 1. Okay, so you can use this easy fact in order to very quickly explain, okay, why does the limit as x approaches 0 of this function does not exist, okay? Because if you go from the right, then the limit should be 1. If you go from the left, it should be 0. They are not equal, okay? So this should be if and only if. Sorry. So you can use this result and immediately explain, okay, why the limit does not exist. Okay, this was a convenient tool because you cannot. Because you don't have to go back to the epsilon delta definition and have to show me, okay, for which epsilon you are not able to find a delta such that I should say for which epsilon you have to give me one epsilon such that no matter how small is delta, there's always a point inside which is mapped outside the epsilon strip. Okay, this would be using the epsilon delta definition. This would be the way to disprove that the limit x tends to 0 of this function does not exist. Okay, but this here gives you an easy shortcut. Okay, you first prove this here using the epsilon delta definition, and then you use this fact in order to show that limit do not exist. Now you see that the reason why you can argue like this is because if you have a function of one variable, there are only two ways how you can essentially two ways how you can approach. Of course, there are more, but there is you can either come from the right or from the left. You could also jump like this. Okay, but this tells you here that if you go this direction, okay, and you get the same limit as if you come this direction, okay, then the limit, the original limit, is also equal to L. Or the way we used it here is if you go this direction and the limit is different from this direction, then the limit will not exist. Okay, and the same you can use here. The same principle you can use here, but you have much more freedom how to choose the direction. Okay, if you find two directions, two passes, and you approach the point AB, okay, along two different paths, and the limits are different, then this limit does certainly not exist. Same principle as here. Okay, so if the limit of f of xy along the path C1 equals L1 and along the path C2 equals L2 with L1 is not equal to L2, then the limit does not exist. Does not exist. Okay, so this is similar as in the one-dimensional case where you approach from the right, approach from the left, and you get different limits. Now you can use this in order to, because our claim was those two limits exist. You cannot use this. You cannot use this. Obviously, you cannot use a principle like this to prove existence of a limit, because then you have to consider every path, and for every path, the no matter how you approach, the limit must always be the same. Okay, it would be too complicated. But you can use this in order to disprove, in order to prove that a limit relation does not hold. Okay, so for this function, I said that if you do some numerical experiments, you choose some xy small enough, you will see it looks like this function, the function value does not approach to any limit. Now, this can be used in order to explain why. Okay, so let's look at this example. We want to disprove that the limit exists. Okay, so we look at this function here. Okay, so we have to approach along different passes. So here is the xy plane. Now, one way we can approach is, for instance, along this line here. Okay, so along this line, y is equal to 0. If y is equal to 0, you see this function always equal to 1. Okay, so here actually the function value here along this line of this function is always equal to 1. So you see that, so call this C1. So the limit xy along C1 of f of xy is equal to 1. Okay, but if you use this direction of approach, okay, which is C2, you see that the limit xy along C2 of f of xy. So you see here you have to plug in x is equal to 0. Okay, so everything will be 0. So here you have 0. Okay, 0. And because those two here are different. Okay, you see that the limit does not exist. X, y both tend to 0, 0 does not exist. You also see that this is an example. If I compute this limit here, the double limit of g of xy, where I first let, let's say, y approach 0, and then I let x approach 0. Okay, so if I first let y approach 0, so what you get here is 1, and then you let x approach 0. So what you can get is 1. Okay, but if you do it differently, if you first let x approach 0 and then you let y approach 0. Okay, so first you let x approach 0, then you get here 0. So this function is 0, and then you let y approach 0, then you get 0. So different from 1. So this symbol here is not just a symbol for computing the limit, okay, the iterated limit. Of course, if the limit exists, those two limits will be the same and will be equal to the limit. But if the limit does not exist, those two might be different, but not necessarily. Okay? If the limit does not exist, those two might be the same, but the limit still does not exist. Okay, we will see an example in a few minutes. Okay, so if you have given such a function, you want to disprove a limit relation. One of the tools you might be able to use is you use different ways of approaching the origin, and you get different limits, and this then disproves that the limit relation that the limit approaches any fixed value. You see, a more interesting example is this one. This one. Now, so again, let's try the same thing. So let's approach along different directions. You see, if I approach here along this direction, okay, then y is equal to 0. So the function is equal to 0. Okay, so if I approach along this direction, okay, the limit will be equal to 0. If I approach along this direction, here the x is always equal to 0, so the function is also 0. Okay. So you see that in this case, okay, if I look at the limit, y tends to 0, x tends to 0 of f of xy is equal to 0. And if you look at the limit the other way around, also equal to 0. So those two are the same, but this does not necessarily mean that the limit exists. Okay, so because you have to check not only this direction, not only this, many others. Okay. Now you see, but yeah, you see, interesting direction is this one. Y is equal to x. Okay, so you approach like this here. Okay. So what does this mean? Okay, so we compute the limit. Now, if I approach like this here, okay, because y is equal to x, so this just becomes a usual limit problem. Okay, x goes to 0 of f of xx. Okay, but this function here, okay, you see, is 1/2. So what you get is 1/2. So actually, if you are on this line here, okay, because the function is not defined at this point here, but if you are on this line, the function value is always 1/2. Okay. So you see that if you approach along this line here, you get 1/2 as the limit. If you approach along this line, you get 0 as the limit. Okay, so the limit does not exist. Okay, so we see that it's not just enough. From this example, which we see, it's not just enough to check, okay, what is the limit if you approach along the coordinate axis. You also have to consider other directions. Okay, because if you just look at the coordinate axis, you would conclude here the limit exists, but in fact it does not because of this line here. Okay, this kind of raises the question whether maybe it's enough just to check lines. I approach along lines. Okay, maybe if I approach along lines and I always get the same limit, okay, one could guess that this should imply that the limit exists. You understand what I mean? No matter how you approach, you always approach along a line. No matter how you approach, the limit is always the same. Okay, does this imply that the limit exists? And even this is wrong. Okay, so kind of you could believe that this is true. Okay, you just approach along lines, but functions of two variables can behave much more complicated. So let's look at an example where no matter how we approach, whenever we approach along a line, we always get 0, but the limit still does not exist. For this, we look at this example. It should be this one. Okay, so let's again check directions. So if we are on the x-axis, on the x-axis here, of course the point which is excluded here is this point here. Okay, so if we are on the x-axis, then y is always equal to 0, so the function value always equal to 0. Okay. Now, if we are on the y-axis, okay, x is equal to 0, so the function value is also always equal to 0. If we choose any other line, y is equal to mx, any line going through the origin, and compute the limit x tends to 0, f of x mx. This means approaching along this line. Okay, then what we get is, okay, the limit x tends to 0. Now we just plug this in here. So what we get is m square x square over, and here we have x square plus, but here we have m to the 4th, x to the 4th. Sorry, here to the cube. This actually is important. Okay, so we see that. Okay, so this m squared is just a constant, but we see that we divide everything by x squared. So what we get is m squared x over 1 plus m to the 4th x squared. And you see this is 0. Okay, so you see that no matter how you approach, okay, if you approach along such a line, no matter how you do it, you always, your function value is not like here's the situation is here on the coordinate axis is different. On the coordinate axis, the function value is identical to 0. But if you approach along such a line, okay, then the limit is always equal to 0. Okay, but still, for this example, this does not imply that the limit exists, because if you choose x is equal to y squared, okay, so if you choose x is equal to y squared, so now you look at the limit. Now y tends to 0 of f of y squared y. Okay, then what you get is y to the 4th over y to the 4th plus y to the 4th, sorry, in the limit. So the limit y tends to 0, y to the 4th over y to the 4th plus y to the 4th, and this is equal to 1/2. Okay, so what you get is 1/2. So actually, and which kind of path is this? This is this path here. Okay, so if you walk along this path, okay, the function value will always be 1/2. Okay, so here the limit, of course, will be 1/2. But if you walk along such a line, the limit will always go to 0. So you see that the limit does not exist. So you see that the situation for functions of 2 variables can be rather tricky, okay? And there are some situations which seem to be seem to be against intuition, like this one, okay? So maybe for this function, maybe it's good to plot a picture and try to figure out, okay, why does the function, and try to see from the picture why does the function behave like this. You find a picture also in, you find a plot also in our textbook. The reason why I still show you this is because you find a very nice plot in our textbook, but I just show you that Maple, it's not so easy with Maple to plot this function very nicely. I'm not sure how the author is doing it, because the reason is if you plot such a the reason is because such a function is not defined at the point 0, 0, but we are interested in the behavior close to the point 0, 0. Okay. Now, if you give Maple such a function and you tell Maple plot it, of course you will get a plot, but around this point 0, 0, and this is where you want to understand this function. Okay. The plot will not be very nice. This is, by the way, the new version of Maple. Maple 11. I'm not sure which version you can use online. Oh no, this is. Why does it look like this? There should be somewhere to. I'm not sure, because now you have a new input mode in Maple, but this is the old one, so let's just use the old one, because we are anyway used to the old one. Now, maybe let's first look at this example, the example I showed you before, or let's directly look at this example just to understand how this function looks like. So as I have explained before, you can use the plot 3D comment in order to plot such a function. Now here the function is x times y square over, and then you have x square plus y square, y to the fourth, and we have to choose a viewing rectangle, let's say from -1 to 1 and y from -1 to 1. We are interested in the point 0, 0 in the origin. Now Vista is very slow, that's why it takes so long. It's not Maple. Okay, so you see the plot is not so bad. This should be the new version of Maple, which makes it better. But but you see that around, if you're getting close to the origin, okay, it's not so easy for Maple to plot the function there, because at the origin this function is not defined. Okay, that's why the plot does not look. It looks okay, but it looks better for Maple 11. It seems to look better than for Maple 8. So if you look Maple 8, you get a more ugly plot. Now you also see here that if you are walking along the parabolas, okay, which are y is equal to x, x is equal to y square. Okay, you see that you are kind of on a ridge. Okay, you are standing higher. Okay, and then there is if you walk along this line, your height is always 1/2. Okay, but you see that if you approach, what you see roughly. Okay, if you approach along a line, then you are walking down eventually. That's the reason why for this function, if you approach 0, 0, okay, the limit does not exist. You see, even from the graph, it's not so easy to see. So that's something where you certainly need calculus. I just want to check. Let's look at the function which I mentioned before, which is much more easier than this one when I talked about functions. This square root of 9 minus x square minus y square, the upper part of an elliptic paraboloid. So from plotted over this rectangle. Normally also for something like this here, because you see that, of course Maple will have problems plotting this, because you see the function is the square root of 9 minus x square minus 9 minus y square. And the domain is everything which is inside the disk of radius 3. But I have to choose here a rectangle as plotting window. So for some points, of course, the function is not defined. So normally you will, if you wonder why the plot is so ugly, okay, you see in particular at the boundary, the plot is very ugly. That's because we are reaching points, okay, where the square root is not defined, and because for the plot 3D comment, okay, the viewing rectangle is the rectangle. Okay, I have to plot it over a rectangle. You see, it will never be easy with Maple to plot this nicely. Okay, it should be somehow possible. Okay, so if you spend a lot of time figuring out how to do it, I guess there is some possibility, because if you look in our textbook, okay, the plot is nice of this function, whereas here the plot is ugly. I also showed you before. I also told you before that level curves can be plotted with Maple as well. I just show you this as well. So apart from this way of plotting a function, you can also plot a function by plotting the level curves. Now, level curves are also called counter curves. So this comment is called counter plot. So you have a counter plot comment of this function. And again, I have to over a viewing rectangle. So let's say from minus 3 to 3 again, and y from minus 3 to 3. you see, this is what I explained before. So you can plot such a function also by plotting the counter at the level curves. You see that what Maple here indicates on such a curve, okay, the function value will be constant, okay, the same. And normally Maple is also using colors, okay, in order to indicate that if you move to the origin, okay, the function value will get larger and larger. So if the level curves is getting more and more yellow, this means that you are higher and higher. Okay, but you see again that at the boundary, of course, Maple has problems of plotting this. Okay, because actually the domain is not a rectangle. The domain here is a disk, and this causes problems in order to plot something like this. So also such level curves can be easily plotted using Maple. Okay, so any questions to this? Okay, so actually I won't need this anymore, so I can move this up. Okay, so you see, looking at this example, you see that figuring out limits of functions of more than 2 variables can somehow be not so rather tricky, because just because of the fact you have many different ways in order to approach here in this case the origin or the point for which you want to compute the limit. Now, but if you find two different passes where the limit is different, then you can use this in order to conclude that the limit does not exist. So we already showed that the limit does not exist here, but for those two we have to guess that the limit exists. So now we should start to discuss, okay, how to prove, how to show that the limit exists, or how to determine limits of functions of 2 variables. Now, the way this is done is just the same as the way we have done it last semester. Okay, so it would be a little bit complicated always to go back to the epsilon delta definition. So once more, the way we have done it last semester is we establish some easy limit relations, we establish some rules, and use the rules to build more complicated limit relations. Now here things fall rather close into line with what we have done last semester. So first of all, you can look at simple functions. Like this one would be a simple function, and you can use the definition of the epsilon delta definition to easily prove that this will be equal to a, and similar for this function. You can again use the epsilon delta definition in order to prove that this is b. Now, if you have a constant function, then the limit, not surprisingly, will be constant, and then you can prove that if you have the sum the limit of a sum of 2 functions will be the sum of the limits, and the same for the difference, and the same for the product, and the same for the quotient. So all those rules, more or less all the limit laws, also hold for functions of 2 variables. In particular, also the rule if you have a composite function. So if you have a function of 2 variables, f of x, y, and you have another function of 1 variable, g, and you consider the composite function g of f of x, y, then if the limit of f of x, y at x as xy tends to a, b tends to L, then and the limit of g of x as x tends to L is equal to some a is not good, to some L2, then also the limit of the composite function exists. So all those rules we are used to from the situation of a function of 1 variable can be used here as well. And this is already helpful in order to, for instance, this example here, because then, okay, so you have the limit xy tends to 0, 0 of this function. Now, Okay, so what you do is you multiply a numerator and denominator by the square roots of x squared plus y squared plus 1 plus 1. Okay, then what you get is x squared plus y squared, and here you have the square root of x squared plus y squared plus 1 plus 1 over, and here you have x squared plus y squared plus 1 minus 1. And then you can erase this one. And for the rest, okay, because as I said, for composite functions, or for a sum, okay, the limit of a sum is the sum of the limits. The limit of this function is no problem because of this property is 1. The limit of this function, okay, is because for a composite function, okay, if this limit exists, then you can actually we have to prove also a law for the square root. Okay, but you see x squared plus y squared plus 1 can be already handled from those two cases. And once you have proved that the product of two functions, the limit of a product of two functions is the product of the limits, and the limit of a sum of two functions is the sum of the limits, then you already can handle this case here just by plugging in. And for the square root, you have to handle extra. But once you know for composite functions that the same rule holds, the same limit law holds as last semester, you know that you can take the limit inside the square root and you just evaluate. Then what you get here is 2. So you see in this case, once you have used the epsilon delta definition in order to prove all the limit laws and these basic relations, you already have, you already know. And this is very similar. This is just the same as last semester, how to determine such a limit. Here for this one, the situation is a little bit different. Now, how to argue here? Because here it would be a little bit more complicated to use limit laws. So how to argue here? How to find this limit, which is claimed to be equal to 1? Of course, you one way to argue, you could say, okay, because I make xy small, okay, if xy is getting small, the meaning of this is, okay, that x squared plus y squared is also getting small, okay. So you can replace this by another variable, omega, and here also by omega, and omega is getting small, okay. And luckily you have here the same function as here, okay. And then we know that the limit, so you can say this is the limit omega tends to 0 of sine of omega over omega, and this one we know is 1, because now like this you can reduce this problem to a so this is a problem for a function of two variables. You can reduce it to a problem for a function of one variable. Okay. Another way to do this is and this is a way which you can use quite often to handle such examples. Is here you look at rectangular coordinates, but because of x squared plus y squared, okay, it is quite natural here to introduce polar coordinates. So if you introduce polar coordinates, okay, then you have this limit relation. And in terms of polar coordinates, okay, the only thing you have to do is the radius tends to 0 and the angle arbitrary, okay? Because you again you have to keep in mind that if you fix the angle, okay, theta, okay, then you again approach here along a line, okay, and then if you just show that the limit exists along every line, okay, this does not necessarily mean that the limit exists. So the theta here arbitrary. But if you plug this in here, then you see that this expression does not depend on theta anymore. Okay, so what you get is here also 1. You reduce it to a one-dimensional problem, similar. Another tool which is so this explains what I told you at the beginning, namely that this limit exists and is equal to 1, this limit exists is equal to 2, and this limit does not exist. So once more, in order to summarize, the limit does not exist. Normally, we try to find two different passes along which the function values approach different values. For proving that limits exist, okay, we use just the same tools as last semester, namely the limit laws. This is sometimes new here. We introduce different coordinate systems, and we will see other examples where this is a rather good approach. So this is something you should keep in mind, that you can, in order to figure out such limit relations, you can, for instance, switch from the rectangular coordinates to the polar coordinates. But you should keep in mind here that because you approach here, okay, you approach x, y, approach to this point here, okay, and the direction can be the path along which you approach can be rather messy, okay. If you introduce polar coordinates, okay, the theta is also important, okay, because this actually is still this looks like a problem of a one-dimensional problem, but actually you still have a theta here, okay. But this does not depend on theta, okay. So that's why you can argue like this. We will see other examples a little bit later. Now, another strong tool which we used very frequently last semester was the squeezing theorem, and also the squeezing theorem holds here for functions of two variables and can be used in order to determine limit relations. For instance, look at this example. This one, limit x y tends to 0, 0, then x times y times sine of y over x squared plus y squared. Okay, so how to handle this? Now, whenever you have such an example, okay, because maybe it's more complicated here for functions of two variables to come up with a guess whether the limit exists or not. Okay, normally you can first try a few directions. Okay, so for instance, if we approach along the x-axis, okay, this means y is equal to 0. If y is equal to 0, you see the limit equal to 0. If we approach along the y-axis, which means x is equal to 0, you see 0 as well. Okay, and then you can try different directions. Okay, you will see that the limit is always equal to 0. Okay, so it seems like the limit should be equal to 0. So this should be then our guess. So this is kind of how you if you've given such an example, the first thing you always should do is you try different directions. Okay, now of course, if you try a couple of different directions and the limit is always the same, this does not necessarily mean that the limit exists. Okay, but at least you know that if the limit exists, this must be the limit. Okay, so for instance, here we know that if the limit exists, it must be equal to 0. Just because of the fact that if I approach along the x-axis equal to 0. Okay, but how to prove that the limit is equal to 0? So our guess is zero. Okay, now for this, okay, so we, as I said, the squeezing theorem also holds here for functions of two variables. So you see that if you look at the absolute value larger or equal than 0. Now what we have to find is some estimate. Okay, so we have here, okay, so this is equal to the absolute value of x times the absolute value of y times the absolute value you could say, okay, this one is smaller or equal than 1. Okay, this is one way you could do it, but this is useless because we saw that the function x, if you do not have this one, we saw that the limit does not exist. Okay, so using that this is smaller or equal than 1 is useless. This we already know. But an inequality which is better is this one. Okay. If you use this, then what you get is this is smaller or equal than absolute value of x y square over x square plus y square. Now this is certainly smaller or equal than. So what I can do is I can if I add here, okay, then I certainly make things larger. So I add here a plus x squared, then I can delete this one. So this is smaller or equal than. Now you see that okay, as xy tends to 0, 0, this of course this function tends to 0, and this function as xy tends to 0, 0 tends to 0 as well. So you see that the limit exists and is equal to 0 by the squeezing theorem. So you see you can use the squeezing theorem here in order to deduce such a limit relation. Normally, if you use the squeezing theorem, what you need is some kind of estimates. Okay, so you have to figure out how to estimate the function. You see, you should do it in the right way, because if you say once more, if you just bound this by 1, which would be a bound, this bound is better because the reason why this bound is better. This bound is not good if y is very large, but this bound is very good if y is very small. Okay, and this is the situation we are discussing. That's why this bound. Okay, if you just replace this by 1, okay, then you also get an upper bound. But this the limit of the upper bound would not exist. We know this already. Okay, so any questions to this? You find in our textbook much more examples where you can try to improve your ability in order to find limits of functions of more than one variable. You see, the situation is a little bit different, so this needs a little bit practice because some of the things which you are used to from last semester are now a little bit different. Now, the next thing, once we have the limit, the annotation for the limit, okay, we will define continuous functions. So a function f of 2 variables is called continuous at the point a, b. If the limit of f of xy as xy tends to ab is equal to, you can obtain the limit just by plugging in. So this means in particular that the function must be defined at ab in order to be continuous. Okay, so this is just the same definition as last semester, and because we have the limit laws, which hold all the limit laws from last semester hold here as well. We can again use the limit laws in order to get similar laws for continuous functions. So in particular, if a function f1, if a function f is continuous at ab, if the function g is continuous at ab, then the sum is continuous as well. The product is continuous as well at ab. The quotient is continuous as well, unless the limit, unless g of ab is equal to 0, unless ab is in the domain, is not in the domain of the function, and so on and so forth. So all those laws we are used to from last semester hold here as well, and then you can use this in order to those laws and the functions which I have discussed before, or the limit laws, the rules which I have discussed before. So if you choose here the function equal to x, then we know that the limit is equal to a. So this means that the function f of xy is equal to x is continuous everywhere, and the function g of f of xy is equal to y is also continuous everywhere. The constant function is continuous everywhere, and you use those rules, and you can easily figure out that polynomials are continuous everywhere, that rational functions, now everything in 2 variables, are continuous everywhere where they are defined, and so on and so forth. So you just have similar behavior. So for instance, if you look at this function which we discussed before, let's say this one, x squared over x squared plus y squared, then this function, because this is a rational function, okay, in 2 variables, So this function is continuous on its domain. So this function is continuous on all points in the plane except the origin. Of course, this, because the origin is not defined, okay, so it's not possible that you have a limit relation like this here. If you look at more complicated functions, like if you use the same function x squared over x squared plus y squared, if xy is not equal to 0, 0, and 0 if xy is equal to 0, 0. Okay, the same. This function is also continuous on this domain here, because we know that the limit, if we approach this function, if xy approaches the origin, okay, that the limit does not exist. Okay. So now, of course, the difference is that the function has as domain all points in the plane, but continuous. Okay, this function is not continuous at the origin. So this is pretty similar to what we have seen last semester. Another example would be the function this function which we just saw before, if xy is not equal to 0, 0, and 0 if xy is equal to 0, 0. So this function would be continuous everywhere, because actually for this I have to prove that this function is continuous. Okay, sine of y as a function of two variables is continuous. Okay, once you know this, you can use our rules. Okay, so because this is continuous, this one you have to prove that it's continuous. Then if you know that the product of continuous functions is continuous, you get that this is continuous. This is a continuous function. If you know that the quotient of continuous functions is continuous, unless for the points where the denominator is equal to 0, then you know that the whole thing is continuous on this domain here. And we know that the limit as xy tends to 0, 0 is equal to 0. So this is how we can make this function, okay, continuous at the point 0, 0. So also here, the point 0, 0 would be called a removable discontinuity, because you can remove it by suitably redefining the function. Whereas here, the point 0, 0 is not a removable discontinuity, because no matter how you define the function will always remain discontinuous at the point 0, 0 at the origin. Okay, so any questions to this? Now, and this I just want to mention very quickly. So we can, of course, we can generalize everything to functions of 3 and more variables. So we will define, for instance, if you have a function of 3 variables, we will define this limit relation as okay, for all epsilon larger than 0, there exists a delta which might depend on epsilon, such that if x and y is close enough to the point, if x, y, z is close enough to this point here, and we use the Euclidean distance to measure this. So for all x, y, and z which satisfy x minus a square plus y minus b square plus z minus c square larger than 0 and smaller than delta, we will have that the distance between f of x, y, and z and L is smaller than epsilon. Okay, similar definition. And then we also call the function continuous at the points, let's say a, b, c, if the limit can be obtained very easily just by plugging in the point into the function by direct substitution. And again, you can again prove that the limit laws all hold for this situation here. The functions f of x, y, z is equal to x, or is equal to y, or is equal to z are all, you can obtain a limit just by plugging in. The constant function, the limit of a constant function is equal to just the constant function, the constant which the function takes on, and so on and so forth. So all those laws you have here as well, also for continuous functions, and you have also the squeezing theorem and so on. So maybe let's look at an example here. An interesting example is this one. An interesting example is this one. Now you see, we want to find the limit. Okay, we want to figure out whether the limit of this function as x, y, and z approaches 0, 0, 0. This is the only interesting point because this is again a rational function, so it will be continuous everywhere if you exclude this point here. So for all other points, you just get the limit by plugging in. So how about this limit? Does it exist or not? And you see that if you go on to functions of 3 variables, the situation is, of course, getting much more complicated because you have much more ways to approach the origin. Again, we could try. The first thing is always to try the coordinate axis. So if you approach along the x-axis, okay, so this means y is equal to 0, z is equal to 0. If you plug this in, you see 0. Okay. If you approach along the y-axis, then you see x and z are equal to 0. So the function is constant 0 there. If you approach along the z-axis, x and y are equal to 0, so the function is equal to 0. So if you approach along coordinate axis, you always get 0. Actually, the function is always equal to 0. Okay. Now, in some cases, you are able to find different directions of approach where the limit is different. Then this will prove that the limit does not exist. For this example, okay, what would you guess? Does the limit exist or not? If I remove one coordinate, okay, before we saw the limit does not exist. You remember, if I remove one coordinate, if I forget about the z coordinate, if I approach along the line x is equal to y, then the limit is 1/2. But if I approach along other axes, the x-axis, the y-axis, the limit is 0. So the natural guess would be this limit does not exist, but this limit exists. Now, how to? This is rather interesting because if you remove one of the coordinates, the limit does not exist. So the limit, as a function of 2 variables, the limit does not exist. But as a function of 3 variables, the limit exists. This also shows you that things can be pretty tricky here to figure out if you talk about functions of more than one variable. Now, how to show that this limit exists? If it exists, it must be equal to 0. Because the reason, once more, because I found already, for instance, if you approach along the x-axis, the limit will be equal to 0. So if this limit exists, it must be equal to 0. Okay, so if you want to have a guess, okay, what is the limit? Okay, what you do is you approach along some path, okay, and if you figure out the limit along some path, okay, then if the limit exists, it must be this value. Now, for this example, the usual way to show that the limit exists is you introduce spherical coordinates. Okay, the reason, the idea behind is pretty trivial because of this here. Okay, because if you introduce spherical coordinates, this will become rho square, where rho is the radius. Okay, so for spherical coordinates, we have x is equal to rho times the sine of what we call psi times the cosine of theta. Then y is equal to rho times the sine of psi times the sine of theta, and z is equal to rho times the cosine of psi. So you introduce spherical coordinates. Now, if you do this, you see that the limit f of x, y, z as x, y, z tends to 0, 0, 0 is equal to, now you plug this in. So for this one, you get rho square. And what you get here is rho to the cube. And then you have twice sine of, then you have cosine of, and then you have a cosine of theta and the sine of theta. Okay, and the limit, now rho must tend to 0, and for psi is always between 0 and pi, and theta is somewhere in between 0 and 2 pi. That's the way you approach, okay? Because you have to choose also a theta, you have to choose a psi, but you approach such that rho is getting smaller and smaller, and theta and psi can behave like this here. Now you see why does this work? Because you can cancel here this one, and then you can use the squeezing theorem. Okay, so you can take here the absolute value, then you have a cosine of psi, you have a cosine of theta, you have a sine of theta. Okay, and this is smaller or equal than the absolute value of rho, because you can all of them you can bound by 1. It's larger or equal than 0. And for this limit, okay, if you take this limit, you see this here tends to 0, okay, because it's constant. But this here, okay, because you see that no matter, because actually you have to consider this as a function of 3 variables, theta and psi. But theta and psi, this does not depend on theta and psi. So if rho goes to 0, okay, this goes to 0. Okay, so by the squeezing theorem, this limit here tends to 0 as well. So this limit is equal to 0. And you see here, for this example, that sometimes for functions of more than 2 variables, 2 or more than 1 variable, 2 or 3 or even more variables, it's not so easy sometimes to figure out what is the limit. It's easy to find. It's easy to have a guess. Most of the time, this proving that the limit relation does not hold is more easy because you have just to find 2 different paths of approach. So normally you will always start by approaching along certain directions and figuring out, okay, what is the limit. If the limit is always the same, then you try several directions, you might be convinced, okay, the limit should exist. And you also have a guess what the limit is supposed to be, because the limit must be equal. It must be equal to the limit if you approach along along one of the passes. So if you always get the same limit, okay, this must be the guess for the limit if the limit exists. So if you approach along several passes and you always get the same limit, you might have the guess that the limit exists, and then you try to prove that the limit exists by normally using something like here. So you see here in this situation maybe quite tricky because you have to come up with an idea like introducing spherical coordinates and so on. The reason why this is normally more tricky for students is because what we have done last semester, limits you have encountered in high school, you are used to it. But functions of 2 variables and more than 2 variables behave in many ways different than functions of 1 variable. More complicated because you have more directions to approach, and this will need some practice. As it needed some practice in high school to get used to limits, this will also need some practice in order to quickly be able to determine whether a limit exists or not and what is the limit. Okay.